So let us start with the 2 by 2 determinants, and probably that is the first non-trivial case that we can look at and get a feeling for the type of problems that we encounter. And once you get through that, get a feeling for that, now we will explore it and do it for what are called n by n determinants. Sorry, n by n matrices. Yeah. So where does this concept of determinants come in? We start with a school level problem, namely solving simultaneous linear equations in 2 or 3 variables, or we begin with 2 variables. So let us consider the system of linear equations in 2 unknowns given by B2, where of course Aij and Bi are real numbers. And x1 and x2 are unknowns. Now these two equations give a simultaneous relation between the unknowns and the scalars Aij and Bi. So these Aij's and Bi are given. Now our problem is how to find x1 and x2 such that, in real, such that they satisfy these two equations. Is it possible to find x1 and x2 such that satisfies these equations? It's a very general question that you are asking. Some specific problems one can easily manipulate. Even this also you can manipulate, and there is a general method of approaching this problem, and that gives the solution in the form x1 equal to, let me just write what is called, okay. So for this purpose we will define a number. One can reframe this problem in terms of matrices, 2 by 2 matrices. What is it? You can rewrite these equations 1 in the form A11, A12, A21, A22, multiplying the vector x1, x2 and giving rise to the vector b1, b2. So the problem is this: given b1, b2, say in R2, okay, the vector b1, b2 in R2, does there exist a vector x such that the action of the 2 by 2 matrix A11, A12, A21, A22 maps that vector x to the vector b1, b2. This is the problem. So essentially the problem is this. See, you have, this is copy of R2, another copy of R2. You have a transformation here. Now call this B. Now we take B as the vector b1, b2 written in the column notation. And then what you are asking is, what is given is this A. A you take as A22 represented by the 2 by 2 matrix Aij. Now what we are looking for is an x such that Ax equal to, does there exist an x such that Ax equal to b? This is the problem. Okay, or more generally, given any b here, is it possible to find a corresponding x here such that Ax equal to b? Now in the process of solving this equation in the conventional way, as we are used to in the school, in the lower classes, that is at school, you see that you will get, so see technically what happens is, this problem is to invert this map. Okay, find A inverse. What is A inverse? This is the problem. Okay, so we will explore that later, but we will go to the conventional way and solving this pair of equations, and it's very simple. Now you multiply the numerator by A22, so A22 A11 x1 plus A22 A12 x2 equal to A22 b1. Similarly, A12 A21 A12 b2. Now subtracting, you get, see, these two terms would go off when you subtract this from this, or this from this. This is what you get. This implies A11 A22 A11 minus A12 A21 x1 equal to A22 b1 b2. Okay. Therefore, you see that a number multiplying x1 is given by another number. I mean, there is no problem up to this. There is no difficulty in getting up to this. Now you see that x1 is uniquely determined provided the multiplying factor with it is not equal to 0. Let if not equal to 0 equal to A22 B1 Similarly, then this is equal to x2 is equal to A11, A21, you multiply by A21, A12, A21, A12, A21, B1 minus A11, A22, A11, B2 delta. Now you see, this is also like the delta that you have got, and therefore let us use a different notation which is more conventional. Let AD minus BC. Which you call, this is called as the determinant of the matrix ABCD. With this notation, we have x1 equal to B1 B2 divided by delta and x2 equal to A11 A21 delta. That is what one does is this, looks at this one, this 2 by 3 matrix, 2 rows and 3 columns, A11, A12, A21, A22, B1, B2. Consider this. Now you see A11, A22 minus A21, A12 is what is called delta. Now what you have in the numerator is this. If you are looking for x1, then replace or strike out the column of the first two columns. Okay, right. This is what is called the Cramer's rule. But that's not the point. Okay, so what you have is you can completely express x1 and x2 in terms of determinants of certain 2 by 2. That is equal to 0, then of course there are all sorts of possibilities. One, there may be, or the equation has no solution at all. That means for any arbitrary b, you may not be in a position to have an x here. Secondly, but however, if b happens to be something special, then this equation is solvable. Now, what that means is this. That is, if you look at this one, these two, this 2 rows and 2 by 3 matrix, and if the first row is a scalar multiple of the second row, then of course the determinant of this is equal to 0. Okay, so that's a special case. But b1 and b2 are not arbitrary then. That means you are looking at a special class of vectors b. Okay, and for those vectors you have not just one solution but several solutions. Okay, so all these explorations can be done, but that is not really our point at this stage. What we are interested in is to look at the definition of determinant. So we have seen that the concept of determinants arises naturally while solving a pair of simultaneous equations, or even more generally a set of n linear equations in n unknowns. Okay, more generally. Now we will come to that later, but before that we will explore this further. So we will confine ourselves to the 2 by 2 matrices. Okay, so that sets the essentially that introduces what we want to call the determinant of a 2 by 2 matrix, which comes very naturally in this context. Now we start looking at this more carefully and mathematically. Okay, so let me look at this problem. So what we are interested in is because it seems it is something which comes up very naturally in the context of solving these two simultaneous equations, and therefore, and also we are going to see that this particular map that you define, what is that map? The map is essentially associating a scalar with 2 by 2 determinants. So what exactly is a determinant? A determinant is a map from the class of 2 by 2 matrices, in this case, to the set of scalars. So we take delta as a map from that is associating with, if A belongs to and A is given by delta is, let me write A is defined by A11 which belongs to R. So this is the map that you have. Okay, but what are the properties of this map? So it associates with each 2 by 2 matrix a real number. It's not an arbitrary real number that you map. However, it is not, does not immediately look like that it's defined in a very simple way. It looks a bit complicated, and it's probably a notation to handle this, whatever that comes in the denominator. We have devised a kind of new definition. I mean, that's what it looks to be while solving the equations. But it has a lot more things hidden inside than what is visible in the outside. So let us explore that. Okay. So let me write A1 let me write A equal to the column vector A to be defined as or denotes A2. Then one thing that you observe is this delta I can write as delta A, I write as delta of A2. That's a new notation, that is putting these things so that when you put them together you get a 2 by 2 matrix, and then you are working on this. So this is not A of this but delta of this. Okay. Now one observes that the following properties. Now you see, this can be considered as, now delta is considered as a map from R2 plus R2 to, or you can even write this. Okay, this is better. R2 direct sum R2 to R. What are the properties? Delta of such that delta of is equal to minus of delta of, that means if you interchange these two vectors, then the value of delta at A to A1 is minus 1 times the value of delta at A1 A2. Okay, this has the simple consequence that, okay, before we do that, we will come back to this, but before that we make some observations. Suppose so let me just write, introduce them or have a look at this. Now you see that we observe that delta of A1 plus A1 prime A2 is equal to delta of A1 comma A2 plus delta of A1 prime comma A2. That means it is linear in the first argument. Similarly, delta of A1 A2 plus A2 prime equal to delta of A1 A2 plus delta of A1 A2 prime. That means it is also linear in the second argument if you hold the first argument fixed. Okay, it's not linear, I mean it's just additive. What I should say is additive. Moreover, you have delta of CA1 plus A2 equal to C times delta A1 A2. So also, when these are little things that you can verify, very easily verified. This further means the following: delta of A1 CA2 equal to C times A2. I mean, these are the properties. See, A1 is a vector, CA1 is a scaling of that vector by a scalar, where C belongs to, for any C belonging to R. Now this property is expressed by saying that is delta is a map in a typical vector of R2 cross R2 direct sum R2 is denoted by A1 A2 to R, which is linear in the first variable when the second is held fixed. Similarly, it is linear in the second variable when the first okay. Now this property is expressed by saying this property by saying delta is a bilinear map on R2. That means it's not as a, see, this is a vector space. It's not considered linear as a map from R2 plus R2 to R. It is linear in the first variable, it is linear in the second variable. So this is one of the special features of this. Now that is, we say that it's a bilinear form. R2. It's a bilinear form of R2. So that is something very interesting. So it's not any number that gets associated. The way in which you compute this, it will become a bilinear form. I mean, there could be several bilinear forms, and this is one of the bilinear forms that you have. What other property you have? Now you see that delta of that means if you interchange the arguments a1 and a2, then this becomes, let me be consistent with the notation. If you interchange a1 and a2, then you see that the value of the determinants changes. Now this is another property that can be easily directly verified. And a consequence of this, hence delta of a1 that's easy to prove, because delta of a1 is equal to minus of delta a1, and that is possible only if delta of a1 is equal to 0. So that gives the proof of that, and this is a consequence of, simple consequence of this. That means if you have two columns of the matrix the same, then the determinant is equal to 0. So these are the two major properties that we have. Hence, we say that we express the property two by saying that delta is an alternating bilinear form on. That is the property that we have. So the first part, 1, tells you that it's a bilinear form. The second part tells you that it's an alternating bilinear form. Okay, that's very fascinating. So it is not that delta is without any special properties, but it has got certain very definite properties which are going to be crucial in our later analysis. Now what we look at is, as it is conventional in mathematical analysis, that we are used to looking at all sorts of alternating bilinear forms on R2. First of all, we observe that the space of now the collection of all bilinear forms on R2 can be as a vector space over the field R. By defining addition and scalar multiplication, by B1 of by defining B1 plus B2 of A1, A2 for every bilinear form on R2. Further, comma, CB C times is defined as C times B of A2. Every C belonging to R, okay, and B belonging to B So what exactly is a bilinear form? Bilinear form is a map from R1 direct sum, R2 direct sum R2 to R with the property that if we denote it by B, then B of A1 A2 is a scalar and such that B1 is linear in the first variable A1 if we hold A2 fixed, and also linear in the second variable if we hold A1 fixed. Okay, so that is what you call a bilinear form. If you consider the space of all bilinear forms, and you can define an addition in this way, it is very straightforward. Now what one has to verify is this. So this is our definition of B1 plus B2 of A1 A2. First of all, we observe that given B1 and B2, B1 plus B2 of A1 A2 is a scalar, is a real number. So it's a map from R2 cross R2 direct sum R2 to R. Secondly, you have to show that this is bilinear. So that is linear in A1 and with A2 fixed, and linear in A2 with A1 fixed, and that is immediately a consequence of the bilinearity of B1 and B2. A simple calculation would help you to do that. Similarly, CB of A1 A2 is equal to CB A1 A2. Is CB defined in this way a bilinear form? That is because that also once again you have to verify. First of all, it's a real number. Secondly, it is linear in A1 with A2 fixed, and linear in A2 with A1 fixed. Linear in A2 when A1 is held fixed, and that is easily verified. It follows from the bilinearity property of B. Okay, so that's very directly verifiable. Therefore, you see that the sum of two bilinear forms is a bilinear form, and scalar multiple of a bilinear form is a bilinear form, and you have got a zero bilinear form. Zero bilinear form is this, is the following, that is 0 of A1 A2, 0 is the definition. R2. So that gives the 0 form. And then you see that all the with this and the inverse of a bilinear form B is given by minus B. That means which maps, if B maps A1 A2 to some scalar, then minus B maps A1 A2 to the negative of that number. That's the definition of minus B. So you can easily verify that it is a linear space structure. So I don't want to spend time on verification of this I leave it to you. But you should understand this concept very clearly. So we have defined what a bilinear form is on R2. And a special case is this. So an example is similarly, you can define B of A1, A2 defined by A11, A22 plus A12, A21. This is also a bilinear form, but this is not alternating, whereas the other one is alternating. Now that's the difference. Is also a bilinear form. Okay, right. This can be written as what? A11, A21. Okay. So that's a bilinear form. So these are examples of bilinear forms. You can construct more examples. But what we are interested in is this delta. Now delta is an alternating alternative bilinear form. This we have defined by the property that delta of A1, A2 that means if we interchange two columns, then the value of the bilinear form changes. So that is what you have. Now one more thing that you observe is that this class of all alternative bilinear forms satisfy form a vector space. A subspace of the space, the vector space of bilinear forms over R. That is another property that you can easily verify, because if you take two alternative bilinear forms, suppose then A1 plus A2 is C1 A1 plus C2 A2 is also an alternative bilinear form. See, all that you need is this follows from the fact that C1 A1 plus C2 A2 of this is equal to, actually this is what you have, C1 A1 of A1 A2 plus C2 A2 of A1 A2, and that's equal to, because these are alternative forms, therefore you have got C1 of A1 of A2 A1 C2 of A2 of A2 A1, and that is essentially equal to minus therefore sum of two such alternative bilinear forms gives you a alternative bilinear form. Therefore, you can easily see that the collection of all alternative bilinear forms on R2 form a vector space. Therefore, one of the questions that you ask at this stage is, do you know more about this subspace, or do you know more about the vector space of bilinear forms and the role of this particular subspace in that. Okay. So I think I will explore that part in my next lecture. So this is once again a starting point for me after a few days of gap. Therefore, once I get into that momentum, I think things will be here. But it's going to be very fascinating. In fact, you are going to see that the determinant is not something very freak and defined in a very complicated way to serve some purpose, but there is some very deep structure which is going to support that. And our objective in this series of lectures is to explore this. Thank you very much. Okay, fine. So that stop streaming.